magnetic field. We're going to find the magnetic field from this wire at the origin, or point O, whatever we're calling it. And so I think the easiest thing is let's just start breaking it up into the individual segments. So I'm going to call this segment that's coming in segment 1, and then this first curved section segment 2, and then as we head radially outward, section 3, and segment 4, the next arced section, and then we go radially outward again, call that segment 5. And we know that the magnetic field is going to be the superposition of all of those. We just add them up. We find the magnetic field due to segment 1, the magnetic field due to segment 2, 3, 4, and 5, and we add them all up, and we get the total magnetic field. So let's take a look at each one. So we're going to use the Biot-Savart law. The magnetic field is mu naught I over 4 pi times the integral of dl cross r hat over r squared. Some books use dl cross r instead of the unit vector, and then in the denominator they have an r cubed. Either way, it's the same equation. So let's take a look. This equation looks a little scary at first. It looks like there's a lot going on here, and you might think it's a difficult one to use. But there are a couple of cases where it is really the best way to go. It's the easiest way to find your magnetic field. And one of those cases is segment 1, when you're in line with the point of interest. So let's take a quick look at why this is the case. I'm just going to redraw segment 1 right here, and then our point of interest is over here. And so dl is some little length of the wire that's carrying the current, and it points in the direction of the current. So I'm going to put dl here. R hat is a unit vector that points from dl to our point of interest. So dl is some little chunk of current, and it's creating a magnetic field at point O. And so here's our r hat vector is going to point in that direction. And what we're interested in is dl cross r hat. And they point in the same direction. So you get a sine of 0 degrees. A moving charge can't create a magnetic field along its line of motion. You have to be some perpendicular distance away from its line of motion in order to detect a magnetic field. And that's the case here. We have charges moving along this wire. We have to be some perpendicular distance away from the direction of motion of those charges. Those charges are moving directly towards point O, and so they contribute no magnetic field at point O. So the magnetic field from segment 1 is 0 at that location. Now if you take a quick look at segment 3 and segment 5, you'll see that they are also pointing either toward or away from point O. So B3 and B5 are also 0 for the same reason. Now let's take a look at segment 2 and 4. This is another case where the Biot-Savart law works very nicely. So let me just write it out here. This is from segment 2. That's what we're interested in now. That first arced section. And I'm just going to redraw it here. We've got this arc, and we're interested in the magnetic field at some point over here, O. That point O is the center of curvature of the arc, and so as we move along, the current is in that direction, and so we can pick some length element that points in the same direction as the current, and that we're interested in figuring out what the, let me just write it out here, the Biot-Savart law, mu naught I over 4 pi integral dl cross r hat over r squared. So dl is some small segment of the current carrying wire, and we want to know what little tiny contribution is it making to the magnetic field at point O, and r is the distance from dl to point O, and r hat is the direction. So there's my direction, and there's my distance, right? And no matter where I am on this curve, dl points perpendicular to the wire, tangent to the wire, and r hat is perpendicular to dl, no matter where I am on this arc, because the point of interest is the center of curvature of the arc. So in this case, my dl cross r hat, that's just the magnitude of dl, the magnitude of r hat, and the sine of the angle between them, right? R hat is a unit vector, so its magnitude is 1. The sine of 90 degrees is 1. So this is just dl. And since it's a circular path, r is a constant. In this case, it's equal to a. So let me go ahead and plug those into Biot-Savart law, and you'll see that this becomes trivial to solve. The dl cross r hat just leaves me with a dl, and the 1 over r squared can come out because it's a constant, and the integral of dl is just the length. The integral of dl is just the length of that arc. So what is the length of that arc? Arc length is just the radius multiplied by the angle if the angle is in radians, right? And so what do we have? We've got a times theta. I kind of went off the page over there. I'll write it over here. Theta must be in radians. And so my magnetic field is mu naught I over 4 pi a squared times a theta. And those two of the a can cancel with one of the ones in the denominator. And this is my magnetic field. This is the magnitude of my magnetic field, but the magnetic field is a vector quantity, so I would have to do put a direction there also. So let's go back up and look at my drawing here. If I run my thumb on my right hand in the direction of the current, then my fingers sort of curl around that. So everywhere to the right of that wire, my fingers are pointing down into the page. I'm just going to go ahead and put some X's over there. This is from, well, maybe I'll do it on this one. My current is going this way. So every place over here, my magnetic field is in. And on the opposite side of the wire, I don't really care about what's happening on the other side of the wire, but I'll draw it here anyway. Over here, in the plane of the page, the magnetic field is coming out. So at point O, that's where I'm interested in, this is going to be pointing into the page. And I'm just going to write it here one more time, theta in radians. Now we have one segment left. It's identical to this segment, so I'm just going to write the answer here. And that's mu naught I theta over 4 pi b, and that's going to be coming out of the page. So B, our total magnetic field at the origin due to all the parts of this wire, all segments of the wire, the whole wire, mu naught I theta over 4 pi, 1 over A minus 1 over B, because they're pointing in opposite directions. And let's see, A is always smaller than B, which means 1 over A is going to be bigger. This is a positive number, so I'll just write into page. Okay, so the idea here, again, you got a big problem, break it up. In this case, using Biot-Savart makes a lot of sense because we don't have, when you use Ampere's law, you have to remember you need long straight wires, infinite wires, straight wires, things like that. It works much easier in those cases. So you didn't really have those here, and you had circular arc lengths, and we were looking at the point at the center of the circle, which is very easy to do with Biot-Savart law, as we saw. And then just add them up, superposition, add up the contributions from each segment.